exponential stuff that we were taught, of which we spoke? What was it all about? What was the point? What was the experiment we ran? You forget.
And I totally kept your penny.
You totally get my penny? You son of a... Paper tuition somehow. So the overriding idea last time was exponential regression modeling. Regression modeling. I mean, honestly, modeling is a bigger idea. Regression is the tool we use to get the model. So we did that yesterday pretty effectively. So how did this differ from the linear and quadratic modeling that we had played with previously to this? We had the linear and quadratic. How was exponential different? How was it similar? I mean, how was it similar? How was it different? We had some, I think there were some similarities and some differences. Cheryl, help me out.
Once you approach 0, it won't go back up. Like
Nice.
quadratic.
Awesome, awesome. So essentially, there's a couple different ways these things look. And the penny data that we looked at last time, awesome, fantastic. The penny data that we looked at last time did kind of this kind of a shape. And I love what Cheryl just said. Once the y values start dropping towards 0, they're not going to recover like the quadratics did. The quadratics had a recovery period after that and headed back up again. Very, very nice. What's cool about some exponential data we'll look at today is they can also go the other way. They can also go the other way. Sometimes that's a good thing, sometimes it's a bad thing. Please,
You said,
Penelope.
you said that it's a consistent multiplication.
First of all, is that your name?
Yes.
Yes! It's a consistent. It was a consistent. Go ahead.
It's a mouthful.
Or
It's
PJ.
Either or.
Okay, Penelope PJ. We're starting to get there. We're starting to get there.
You said it's a consistent multiplication of the first product.
Nice! So that, very, very nice. So the difference in mathematicalness-ishness about it is how you can identify it numerically. We'll come back, let me come back to that, Penelope, just in a second. So we've got this constant multiplication, which is kind of, if you will, visible in the graph, but it kind of hides in the graph a little bit. So what I want to do is, I want to revert back to equations momentarily. Equations do help us. I know that sometimes I write an equation on the board, we start getting like hives, we start breaking out shingles and stuff. But they do help us kind of explain what's going on. So I'm going to put an equation in exponential form up here, a general one. A times b to the x. Now what's cool about equations is this describes what Penelope just said perfectly. This is exactly what she said. Repeated multiplications. What part is being repeatedly multiplied in that equation? Which variable? B. The base is being repeatedly multiplied. So if you think about this, you're going to have a series of x and y values. And we'll go in general first, then we'll come back and look at it more concretely, because I think that's where it makes the most sense is through concrete analysis. But it doesn't hurt to generalize first, and you can't. There we go. That's a little better. So as we let x's go from 0 to 1 to 2 to 3 to 4 to 5, okay? The y values are going to be found by sticking these values into that little relationship up there. This is probably great from your guys' way in. Let's put our GGG down there. Good. So if x is 0, the y is going to be a times b to the 0 power. And what's that going to equal? This is going to equal 1 times a. So it's going to be a, isn't it? Yeah. And whatever a is, a might be 1, but whatever a is, it's going to be that value a. Remember what a was in our penny data from yesterday?
38.
Good. It was 38 because there were 38 of us at the beginning. 38 of us at the beginning before we started flipping. 38. Now when we did the regression, remember what the TI said it was? It was 39. It was 39.2, I believe, but 39, we rounded up to 39. And that's because it's a best fit regression, just like quadratics and linear. Not a perfect fit, but a best fit. Very nice, very nice. Cool. Then we flip once. And so the relationship looks like this. A times b to the first, which is just a times b. Now, I'm going to try to get specific. So yesterday's examples. What happened after we flipped the coin the first time and then checked to see what we got? What was the question I asked? How many people got heads that time? Roughly how many of you raised your hand? Roughly half of you raised your hand. Because here's BJ's repeated multiplication starting to kick in. Remember what B was equal to yesterday?
0.48.
Say that again.
0.48.
Awesome, Gabe, which is essentially equal to what?
Half.
It's about a half that you guys just said. So the B yesterday was a half. So you took our original value, which was 38, and essentially multiplied it by half, and that's why we ended up with roughly 19 after the first flip. Half the class fell away. Half the class fell away after the first flip. Fair enough? Then we said, okay, those of you that were still there. Now remember, those of you that were still there are right here. That comes down here. I'm going to make this a little bit bigger. The remainders come down here, A times B. And what did I have you guys do that still had heads? You flipped again. So what's going to happen is we're going to apply that repeated multiplication of B to who remained. So it's A times B, which ends up being A times B squared. And this is why they're called exponential functions, is because the variable is the exponent. And that's what makes it kind of cool. Your variable is the exponent. Your variable is the exponent. Does that make sense? Ish. You're getting there. You're getting there. Your variable is the exponent. That's what's kind of changing. That's what's kind of changing. So, now how many of you were left? There were 38 originally. Let's just say that was the whole class. The whole class flipped the pennies. After one flip, how many of you had flipped heads? Half. After the next flip, how many of you were left? A quarter. That's a repeated multiplication. A half of a half is a quarter. And after the next flip, how many of you were there? An eighth, because a half of a half of a half is an eighth. And then after the next flip, how many? Because a half of a half of a half of a half is a sixth. And you see what's going on here. After three flips, it goes A times B squared, which was the result after 2, halved again. So you end up with A times B cubed. And I think you're seeing the pattern now. Essentially, you start with this initial amount A, whatever that is, A. And then you start multiplying successively with each increase on the X value. Now what was happening there, we had what's called an exponential decrease model going on. Because the value of B was fractional. It was bigger than 0, but less than 1, so half. It said 0.48, as Dave said, by the regression. But literally, you could think of it as a half, because you were losing half each time. So I want to make a little bit of a sidebar note, because there's two kinds of exponential models that are worth talking about. Here's your general exponential model right here. Do a line right here. Just pull it back. So I'm going to put two ifs. If that value of B in there is, let's do this. If it's bigger than 0 but less than 1, can I write that like that? Does that upset anybody? Actually, I shouldn't say I just did write it, so I guess I can write it. Is it okay to write that like that? If I put B between 0 and 1, does that make sense to you guys mathematically? So essentially, you'll think of B as a fraction, but it's a special kind of fraction. It's less than 1, but positive. So give me some examples. Throw out some. Half is 1 for sure. Give me another one. Another fraction that satisfies that. 3/4, a quarter. Very nice. 3/4, a quarter. 16. A 16th, an eighth. 2/3. 2/3. 0.7. 0.7 satisfied? Yeah. Is 0.7 okay? Because 0.7 is a fraction. 7/10, right? Good. So we understand that. Okay, good. Then we are modeling exponential decay. I always think of the word decay, think of teeth. But exponential decay, which means your initial value is getting smaller with each successive iteration. We're losing essentially 50% of the class every single time we flip the coins. We're also leaving 50% behind, aren't we? So when we think about our model yesterday, it was an exponential decay model because as we go left to right, as x increases, the y values are decreasing. That's why it's called decay. The average rate of change is negative. Think about average rate of change. Can we still talk about average rate of change? You guys are totally pissed and tired of talking about that. We okay with average rate of change, talking about that? The average rate of change is negative because as your y values go down, your x values go up. So think of it from a slope point of view. If you were to connect the dots, making a secant line, I think that's the term we use, a secant line, if you were to connect these dots and make lines out of them, what are the slopes of those lines? What kind of numbers are they, slopes of those lines? They're all negative. They're getting, as we move further right, what? Say that again.
Less negative.
Less negative. Are they ever going to go positive?
No.
Why can they never go positive, Cheryl? Yes, you do, because you said it earlier. The only way they could go positive is if what happened? Well, if it goes past 0, technically they're still getting negative. But what did you say would never happen?
It would never be a parabola.
Right, and that's the only way to go positive, if they started going back up again. Because that means the y's would be increasing as the x's, but it's never going to do that. Not on this curve here, on an exponential decay curve. So I want to analyze yesterday. I want to analyze again, one more time, the penny results from yesterday. Then I want to run a new model of exponential growth and compare and contrast both of them, okay? And then we're going to do, I have a whole bunch of examples. We'll run as many as we have time for today. Most of them are dealing with finances, which I think is an important thing to look at, especially from students and student loan points of view. So I got some data we can play with.
Wait.
What? No, sorry.
Yeah.
Go ahead.
What did you say about the x and the y values? If one is increasing or decreasing?
Well, I'm just from a general slope idea, rate of change. On this exponential decay model, this is a decay model, as x's get bigger, y's are getting smaller. So that's why the slopes can't be positive. If one variable is going down, getting negative, well, one variable is getting positive, negative divided by positive is negative. Slope's negative, average rate of change is going. It's trending towards 0. It's trending towards 0, but it never gets there because you keep taking a fraction of what's left. Now, I know we ran into a problem with that yesterday, didn't we, when we tried to model it? Because you can't plug in y equals 0 to your modeling. Your TI won't let you plug in y equals 0 because you can't actually get to 0 exponentially. You can keep taking a half. There's an old paradox. I think it's called, is it Zeno's paradox? I think it is. If I drop this pen, it will never hit the desk. If I drop this pen, it will never hit the desk. Why? Because it first has to fall half the distance. Then of the distance that remains, it has to fall half that distance. And the distance that remains, it has to fall half that distance. And then it has to fall half that distance. And then half that distance. And then half this distance. So if I have to keep taking halves, what am I never going to get to? 0. But we know that when we drop the pen, it hits the damn desk. That's why it's called a paradox. The limit of 1/2 to the n power as n goes to infinity is equal to 0. It's defined in terms of what's called a limit in calculus. Anybody taken calculus before? No? It's a wonderful idea. It's a wonderful... So I heard some grains and some dry heaves over here. I apologize. But the idea is that you can examine the behavior of this curve. This curve flattens as x goes off to infinity. But it never truly flattens. It trends toward flattening. As you said, Cheryl, these slopes get less and... Actually, no, Brady said it. These get less and less negative. They never actually become 0, but they get as close to 0 as you want them to be. So that's what's kind of cool about exponentials. They have that trailing off towards 0 that you mentioned before. And that's exponential decay. I want to analyze just one more time the equation from yesterday with the penny flip, just looking at it from a percentage point of view. Let's come over here. So we'll get some examples together here. Examples. Okay, so one was the penny flip. And Gabe, I love the fact yesterday, penny flips, you made us regraph the perfect equation with the regression equation. That was so fantastic because I like to compare and contrast both and see how well the exponential models fit. So let's do penny flips both ways. We had the regression equation, which I think I got this right. It was y equals 39 times 0.48 to the x. I think that was what it was, right? Okay. So what I want to do is I want to analyze both pieces, both numbers in that equation to make sure you guys walk out of here today understanding what a and b always are. What a and b always are. Because the exponential models are among the most beautifully simple of all the models. There's only there's two constants. The a value and the b value. It's like a linear model. But this is, for some reason, exponentials seem to be a little bit more straightforward to understand. So I want to make sure you guys understand it. This number right here, this 39, usually has one of a few different names. I like to think of it as the initial value. It's the initial value. So what do you think I mean by initial?
First.
Say that again.
First.
Good. When you start an experiment, it's how much stuff you have at the beginning. The first value you play with. It's your first y value. I like that. I'm going to use that if you don't mind, Cheryl. It's your first y value. At the start of your experiment, before you start messing with whatever you're doing, your quiz that I posted for next week involves rolling a die, or simulating rolling a die with your TI. So you've got a number of dice, and you roll them all until you get, I think you roll until you get a 6 or something like that. So you 30 dice to start with, A would be 30. 100 dice to start with, A would be 100, whatever. We'll get to that. We're going to talk about the U.S. population here in a second. 0.48, this is the percentage that remains after each. Can I use the word iteration? Or should I not use the word iteration?
What does that mean?
Okay, let's not use that. Let's say after each step. It essentially means step. Let's not use the word iteration. If anybody asks what it means, that's not a good word to use. So basically, it's the remaining percentage after each step of the experiment. So in other words, after step 1, 48% of what was there originally is still here. After step 2, 48% of what was left after step 1 is still here. At step 3, 48% of what was left at step 2 is still here. Does that make sense? It's back to PJ's repeated multiplication of 0.48. But if it's okay with you guys, I want to uber analyze that 0.48. Because if there's 48% remaining, what went away? Say it loud and proud. 52% went away, right? So this 48%, the way I always like to look at this, and because we're Americans, we suck at this, just so you know. Because we're Americans, we totally suck at this. Okay, I'm going to come over here and rewrite this equation in an equivalent but slightly different looking way. Y equals 39 times 1 minus 0.52 to the x. I'm sure this pisses you all off right now. That's okay. That's okay. Because you're like, why are you making it more complicated? You're making it more complicated. No, I'm not actually. I'm making it more understandable. It might not feel like that right now. This 0.52 is the percentage removed at each step. Yes. What does the 1 stand for, friends? What do you think the 1 stands for out here? Think in terms of percentages.
100.
It's 100%, which would be 100% of whatever you have at each step. At each step, whatever you have. Now remember, that 100% shifts. Because of PJ's repeated multiplication, each step's 100% is smaller, or you'll see soon, bigger, potentially, than it was originally. So you've got 100%. This is the 100% that each step starts with. So all I'm trying to do is I'm trying to make you guys understand. When you see an exponential decay model, actually take that back. When you see an exponential model, the percentage that's in there tells you how much remains at the end of each step. 48% remains, that means you must have gotten rid of 52% of it each time. Is that fair? Is that ish fair? Yes? Okay, good. Ish. Good, decent? Okay. Let's look at one more of these models, a decay model. And then I want to go the other way and look at a growth model too. Because growth models are cool as well, and they have lots of applications. All of these things have cool applications, which is pretty freaking rad. But the decay models generally seem to be a little more doable because, as Cheryl pointed out, they go down to 0. They eventually zero out somewhere. Whereas the growth models start at 0 and then explode up exponentially, exponential growth. So I want to look at, I'm going to have you guys do a question eventually about my old lead singer who used to drink 3 Red Bulls at a time. And we're going to talk about how his liver is probably not going to last till he's 50. But the idea is your liver is a filter. Your liver filters. And the idea of a filter is you pass impurities through it, and then it gets rid of a little bit at a time. And it's essentially exponential. It's essentially exponential. So can I go, we'll do a second example here. I'll go over there, I think. Let's talk about Any of you guys have ponds on your property? Or large bodies of water, like either like irrigation ponds or water features, things like that? You guys have ponds on your property. You have filters on them. Okay? Why do you have filters on them? Do you guys have fish in them? Let me ask another question. Are there fish in the pond? Is it just for irrigation?
No, it's just a little teeny.
Oh, it's not big enough to have fish. Do you have the frogs singing yet?
Yeah.
Oh, isn't that great? Have you guys heard the Pacific tree frog singing?
Yeah.
You can tell spring's here. Bleep, 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 all night. Trivia. Anytime you hear frogs chirping in a movie, it's those. Yeah, have you ever noticed in movies, there's certain nature sounds you hear a lot. Like you always hear Stephen Colbert, watch Stephen Colbert shows and all. There's that sound of the eagle. That's not an eagle, that's a red-tailed hawk. Anytime you see any bird of prey on a TV show, they always have a red-tailed hawk. Because all the other birds of prey sound, you know what an eagle sounds like when it makes a noise? What does an eagle sound like? It sounds like a broken saw. It's ridiculous. Like, this is our national bird. It sounds like it's stuttering. So they use a red-tailed hawk. Frogs, whenever they have like a serene frog sound, it's our little Pacific tree frogs. Those little males with those big vocal sacs chirping. You seen them out there at night? They're pretty easy to find because they're so damn loud. And they chirp right until you're next to them. And then if you interrupt them, like while they're in mid-chirp, their throats are all out like this. And they kind of look at you. Anyway, I was talking about that. Oh, this is the point. There was a point to that. Filtering. Thank you. Filtering. Because you have. So we also have ducks in our pond to visit. You guys have ducks to visit your ponds? It might not be big enough. If you have a large enough pond, the ducks will find it. And they poop in it. They poop in it. They drive the pH up. So you put filters on your pond because you don't want your water to turn into a cesspool. So the way filters work is they remove a certain amount of impurities per unit of time or volume. So let's create a fairly realistic filtration example. So let's talk about filtration. Filtration. You can view filtration as an exponential model. You can also view it a couple different ways, but an exponential model is a pretty fair way of viewing it. Okay? So let's say filtration. Let's say a pond filter removes. Let's say it's a pretty efficient filter. Let's say it removes 45% of impurities each hour. Let's say a pond removes 45% of impurities each hour. What's going on, my friends? Something confusing? Something that's confusing.
What happens in 48%? That was on the first
It's a different model.
Oh yeah, this is just a completely different example. Example 2,
Oh, okay.
filtration. And you know what, Lynn, that's a good point. Let's make it something else besides 45. Let's make it,
No, I'm sorry.
I wanted to remove more than that anyways.
okay, how about 70?
Perfect.
Good. It's a crappy filter. Make it 70%. Make it 70%. That's good. That's good. 70% impurities after each hour. Fair enough? Fair enough. Okay. How long do we have to wait? How long do we have to wait until we're down? Weird. To less than 1% of the original impurity level. So in other words, you've got an issue with your pond. You've got a bunch of crap, duck crap, fish crap, algae, overriding bacteria. Your neighbor's dog likes to bathe in there. Cat hair. Actually, you wouldn't have cat hair in your pond unless your cat likes to swim. And this is a little bit fictitious because chances are, if you put a filter on your pond, you're still going to have impurities coming in and adding to it too. But let's start with a slightly fictitious example first. In that, as soon as you put the filter on the pond, the impurities stop going in, and you're only getting them out using the filter. It's a fair bit fictitious, but if we understand this model, we can understand the bastardized exponential later, which will add to increasing and decreasing at the same time at different rates. With me so far? So how long is it going to take? How long is it going to take, do you think? What do you think? What makes this a challenging problem? It's a challenging problem, isn't it? Kurt,
Well, you're taking 70% of what's remaining each and every time, so I don't know how to end up with less than 1%.
Good. Awesome. Scott, good. Thank you for that, Kurt. Very, very good. Scott, go.
But aren't you, if you have 100%, you take away 70%, now it's the 30%. So it's 70% of 30%, and then it's 70% of
That's what I'm saying.
like 20% or 21%.
Whatever's left, you've got, that's what we have to model right then. We have to model that right there. We've got to basically set up this exponential model based on this new situation. Did you hear what Scotty said? First of all, Kurt's point is 100% correct. Yeah, okay, after 1 hour, 70% of stuff is gone, we're down to 30. How about the next hour? Well, that's where PJ's repeated multiplications come in. We have to repeatedly multiply by a certain point.
30% of 30?
30% of, well, it depends on which step we're at. See, here's the thing. It depends on which step we're at. It depends on which, let's make a chart. Let's organize our thoughts. I think this might be the way to go. Instead of just trying to do this in our heads, let's organize our thoughts like we did over here. I think this might be a good way of attacking it, yes? What do you think, Shane?
Can you read the question?
Oh, I'm sorry, these damn wide rooms. So, we got a filter. It's knocking out 70% of impurities every hour.
Right.